Happy Friday.
Yeah.
My kids don't have school at all next week, I'm so envious.
Oh, wow. That means you gotta do double duty, right?
No, my wife's back, so it's actually works out better for me because we can come and go as I please. Told anybody around. Okay, I saw Hussein. He said he's going to be a little late, so I'm going to go ahead and start. Okay, so last time we were continuing our discussion on Yukawa theory, and we had picked it up. We had just computed like our first real amplitude, and one of the things that we were wanting to address, or still needed to address, was this issue of signs. You have external fermion lines. And so we took a look at that. We looked in particular at one scattering amplitude for fermion to fermion goes to fermion through the scalar interaction, Yukawa interaction. And so we were trying to figure out how we could figure out the relative signs, right? If you have multiple Feynman diagrams that contribute to a process, how do you figure out those relative signs? Because, like I said, if there's only one Feynman diagram, you can forget this whole discussion. You don't even have to worry about it. But in cases where you have identical particles in the final state, you know that there's going to be this kind of identical particle, problem that you have to deal with. So we looked at one particular diagram, which we wrote down as a contraction like this. And to kind of clarify, or to make more clear what the signs are relative to other diagrams, we kind of came up with this little prescription where we try to untangle the lines. In other words, we move the fields around until there's none of these lines cross. Okay? And so we looked at a particular case, this guy, I think, where we moved, we noticed that if we can untangle it, if we take psi bar and move it through two of these fields, right? And that would untangle all the contractions. But when we move it through there, we pick up two factors of -1, but that just gives us 1. Okay, so there the sign doesn't change. But then we consider a different contraction, right? Contracting the fields with the initial and final states in a different way. And there we saw that we only had to move this psi bar once, right? We had to move through the psi of x, and then that gives us an untangled diagram. So in that case, that diagram will give you a minus sign relative to this diagram, however you want to define the overall sign. All right? And so that other diagram, like I said, it corresponds to this diagram where you have the final state particles crossed. Okay, and this is the case. You'll run into this case anytime you have. What's it doing?
He's messing with it.
Oh, okay. Did you know you're controlling the magnification?
Yeah.
Okay.
Actually, I'm trying to crank up the volume, man.
Oh, okay.
Sorry.
That's all right. I just saw it. I just saw it moving.
Trying to do?
So anytime you have this case where you have identical particles in the final state, you're going to have to consider these cross diagrams, okay, along with the original diagram that you wrote down. So to the full result for this case, when we're considering, say, fermion to fermion, we've got this diagram, and then we've got the cross diagram. And with our prescription, the minus sign goes with the cross diagram. Okay, so you can imagine that you could do your prescription in a different way where this guy would get the relative minus sign. It doesn't matter, okay? Because in the end, like I said, it's modulus squared. So the main point is you just want there to be the relative minus sign, okay? And as we've seen, this minus sign difference is due solely to Fermi statistics because fermion field is anti-competitive. What did we do then? Then we looked at more complicated cases, right? And we found that, or we saw that basically we could move pairs of bilinears through each other because those things do commute, right? So if you have a long string of these things, you can move them around and get them in a particular order, and then just write down a string of Feynman propagators. And the special case, where you have this kind of the situation are closed loops of fermions. Right? So diagram here we have a fermion loop which closes in on itself. Okay, and there we found that there's a general rule, right? When you move the stuff around to get everything in order, it's always the trace of the propagators or any vertex factors that are inside of here, and you always get a minus sign. Okay, so we said the general rule is that anytime you have a closed fermion loop, you have to include an overall minus sign for that diagram, and you have to trace over the propagators that are in that loop. Okay? So for example, I worked out this little self-energy diagram for the scalar field. Right, so like I said, I always like to, when I write down a closed fermion loop, the first thing I do is write a -1 inside of it, just to remind myself. So this is the -1 from that. Here's the two vertex factors. And then these are the two propagators, the two fermion propagators, and I'm taking the trace over them. Okay. All right, so from there we said, okay, that's Yukawa theory. So it describes the interaction between fermions and the scalar field. Right? Scalars obey Bose-Einstein statistics. So then we wanted to try to generalize it to a vector boson, right? So generalize the interaction of fermions to the interaction of a vector boson. And in particular, a very special vector boson, the photon. Okay? And this is what's known as quantum electrodynamics, or QED. And to go from Yukawa theory to QED, you can, like we started to, you can kind of hand-wavingly just make a nice little generalization. It's not as simple as this, okay, in real life. I mean, you have to, if you go look at Schrodnicki, for example, I mean, he works out the path integral for vector bosons, and you see that, there's some intricacies, but what we're going to do here works, okay, and that's what we want. We want something that just works so we can go off and start making some predictions. Okay, so we'll generalize the interaction with Hamiltonian, right, from what we had in the Yukawa case to this case, all right? So here, A mu is the quantized electromagnetic field, in other words, the photon, right? And because it's a vector field, it carries this Lorentz index, and so we need this, the Hamiltonian to be a scalar, so we have to dot it into something, right? And the way we do that is to dot it into this thing, this sidebar gamma mu psi, which we know will come to know as the fermion current, or the electromagnetic current. All right, so we'll dot the A mu into this vector button here. Okay? And then we just kind of walked through how the Feynman rules change. So the vertex basically stays the same as what you had in your Yukawa case, except now you've got this extra Dirac matrix, right? Or this Dirac matrix. The photon propagator looks basically like the scalar propagator, except you have this G mu nu in here, and I'll talk about that in a little bit. And for cases for external fermions, where you say you scatter E plus E minus into two photons or something like that, where you have external photons, you have to write down a contraction rule between the photon field and the external, or initial and final states. And those we write in terms of the polarization vector. Okay, so we wrote down these rules, and then we tried to justify them. Okay? And the way we started to justify it was to say, well, we want theory that's Lorentz invariant, so let's work in the Lorentz gauge, which you learn about in classical E and M. And there you see that you basically, you have this freedom to choose your gauge. I don't want to get all into the mechanics of.
Yeah, we know.
Yeah, okay.
We talked about it in.
Okay, good. So you have a choice, okay? So we're going to work in this gauge. And in this gauge, you see that all four components of the vector field satisfy something that looks like a Klein-Gordon equation. Okay, so something for a massless boson. Okay? So we see that it satisfies massless Klein-Gordon equation, so we can kind of guess at its solution, right? So that the fact that it satisfies the Klein-Gordon equation tells us that it has a wave, a plane wave part. And because it's a four vector, we have to, kind of glue a four vector onto this solution that we just happen to call epsilon, right? And then as you go along, you know that p squared has to be 0 because you want the photon to be massless, right? So the photon, an on-shell photon has to be massless. And at this point, this was any four vector. And this is exactly what we did for the case of the Dirac fermions. Okay? And then you try to make a connection, right? You always do this. You write down your quantum theory, and then when you try to make sense of it, you try to make a connection with classical physics. Right? And so in this case, we'll make a connection with classical E and M by saying, okay, this epsilon, this arbitrary vector, let's identify it as the polarization vector, okay, and work out the consequences and see if it works. Okay. And so that's that, right? So we can write down a solution, or we can write down an expression for the photon field. And at this point, it should look familiar, right? So we've got the positive and negative frequency wave parts. We've got annihilation and creation operators, and then finally we've got the four vectors that we identified with the polarization vectors. Okay? So in that case, you can justify, these Feynman rules that we wrote down for external photon lines, because you can go through the same arguments that we did for the scalar case and then for the fermion case, and see where these factors come from. Okay. There's one subtlety, and that's the fact that we have photons that have to be transversely polarized. So that means that P dotted into the epsilon. So P here is the 3 vector. When you dot P into the polarization vector, it should get 0. Right? So there should be no longitudinal polarization. And so that just means that you have to make sure that your polarization vector takes the normal form, at least the three component parts of it, right? And so for right or left-handed polarization, just as an example, you could write down a polarization vector that looks like that. Okay. All right, so I think that was about where we stopped, where we got interrupted.
Yeah, I think so.
Okay. So let's continue on with our justification of the Feynman rules that we wrote down. Okay. So probably the easiest one to justify is the vertex rule, right? And that just comes from inspection. Okay? And a lot of times when you're, in the real world, and somebody hands you a theory, you can basically read off the vertex, what the vertex rules are, okay? Because they kind of, you've got a fermion, an anti-fermion, and a photon, and then there's some gamma matrix structure, typically, right? It gets a little more difficult. Sometimes there will be vertices that have derivatives, that have 4 derivatives. Those are a little tougher to figure out, but for the most part, in any theory, when you look at the vertices, you can just read off the Feynman rules. That's the easiest part. Okay. Word of caution, though, when you write down, these factors of gamma mu coming from vertices, they have to stay in place. Okay, so they're not like constant factors that you just pull out, out in front. They're going to be, because you're going to be, as we saw last time, when you write down the amplitude for some fermion scattering process, you trace along this line, right? So you would assign some factor of u bar or something up here, and you would trace down, then you hit this vertex, and that would give you a factor of gamma mu, right? And you got to keep that gamma mu in place, right? And then you would come down and you would have a factor of u.
We used to just collect them all out in front, right? Like if we had 3 vertices, it would just be.
Yeah, because we always had scalar couplings, right?
So now we have to keep them.
Now you have to, the coupling part, this IE, you can pull out front. That's just the number. But these are matrices,
Yeah.
right? So you can't just pull them out in front, okay? So you have to be just a little careful, but you'll get used to it. It'll become second nature, okay? But just know, that because these things are, the same, the amplitudes that you write down, that like we saw last time, are just basically a string of matrix multiplication, right? You have to keep the gamma values there. Right. Oh, and the way we've written down the rule here is it's for specifically for electron-positron pair, but you can generalize this rule to any charged particle, right? So maybe it's the up quark or the down quark, which have charges of 2/3 and -1/3, right, respectively. So there you would plug, you use the same thing, but you'd use a factor Q, and that Q is the relative factor, for the charge, right? So for up quark, it'd be 2/3 or something like that. Okay, all right, so that's the vertex. And as I told you guys earlier, unfortunately, there's no easy way to derive the photon propagator, and you really have to, even Peskin waits until he talks about path integral formalism, which he doesn't do until like chapter 9 or 10. And that's where he works out the photon propagator. Okay, so you really need the mechanics or the tools of path integral formalism to be able to compute this thing. But you can kind of piece it together just by the stuff that you know, right? And the first piece, we've already seen that this photon field in Lorentz gauge satisfies the massless Klein-Bordern equation, right? So that should be no surprise that the propagator, at least the denominator part, looks familiar, right? It's like p squared. There's no m squared because it's massless now, right? But it's p squared, plus I epsilon, if you don't like that I epsilon piece. Okay, so the denominator we can understand, right? The factor of minus g mu nu, that takes a little more work, a little more explanation, right? And it turns out that Lorentz invariance requires that the photon propagator be something called an isotropic second rank tensor, okay? In plain language, it just means that, photons are going to be going from one vertex to another, right? Typically, and when they're internal, okay? So that's when the propagators come into play. And at each vertex, you're going to have a gamma matrix, right? But you want the amplitude to be a scalar, right? So that means that the photon propagator has to have something that will contract out those gamma matrices, okay? So in general, you could write down, so there's a couple of choices that you have. One is, so you want to rank 2 tensor, right? So you could use G mu nu, or you could use a product of, say, the photon's momentum P. So it'd be like G mu nu, and then there would be a term that would go like P mu, P nu. Right? That would also contract out those gamma matrices and the vertices. The problem with the P mu, P nu pieces, those correspond to longitudinal polarizations. Okay, so we have to drop, so we can't use those for a photon, but we'll see when we get to massive vector bosons that those terms in the propagator do contribute, okay? So in general, you just need a second rank tensor, and the only one that we can really use, and I say here the simplest candidate is just G mu nu, right? But it turns out that there are a couple of choices, but this is the only one that corresponds to a transversely polarized photon.
This G mu nu is metric tensor?
Yes. Okay. Yeah. Minkowski metric tensor. Yeah. And finally, so that's the G mu nu part. The minus sign. Where does the minus sign come from? Well, that turns out to be an issue with the normalization of our states. Okay, so let's look at the propagator of the photon and take the Fourier transform of it. Okay, so here's the fermion propagator, and I'm taking the Fourier transform. All right, so that means I have to do this integral over q squared, and I get something that looks like this. right? And this is nothing but, so that here we're in, this should be, we're in position space, right? So it should correspond to what we would call this time ordered product of two A operators, right? Two photon field operators, okay? Okay, and so what we want to do to try to figure out where this sign comes from, or why we have to have that sign there, right, is let's set mu equals to nu, okay? They're not contracted, but we're just setting mu equals to nu so that they're the same state, right? And we'll take the limit that x naught and t and y naught are the same, okay? So in other words, that these things are at the same time, okay? So what that all means is that this thing should become something that looks like this, right? And this thing is just the norm of our state, right? So this would be like, we have a state that we, create with a mu, right, at x, and we dot it into itself to compute the norm, okay? Right? And so what we want is, anytime we compute a norm in quantum mechanics, we always want this thing to be positive, right? And so for the I equals, or the mu equals I pieces, so the 1, 2, 3 pieces of the 4 vector of the metric tensor, we need the minus sign because why? Because g mu nu becomes, in this case, we're taking the limit mu goes to nu or nu goes to mu, so we're taking the diagonal pieces, right? And the diagonal pieces, the I pieces, are negative. Right? We're working in the East Coast metric, so it's plus, minus, minus, minus. And so if you want a positive norm, you have to put that minus sign in by hand, the way we're doing things. Okay, it would come out naturally if you were doing things in the pathetical formalism, but just piecing together things by hand, we have to put this minus sign in by hand because we want a positive norm. Okay. Okay. Now you might ask, well, okay, so that explains the spatial pieces. Well, what about the time pieces? Well, it turns out that the time pieces are troublesome. Okay, and they actually, the g mu nu is not positive definite, right? So the states created by the time component of your field actually have negative norms. Okay, but what we'll show later on is that this doesn't cause anything, any serious problems for observables. Okay, so it's not a, theoretically it's troubling, but we'll see that in the end it's not a problem. Okay. Okay.
You sweep it under the rug.
Mm-hmm.
You sweep it under the rug.
Well, exactly. That's what we do. Okay, so before I move on to start to talk about how to compute stuff in QED, I thought it'd be interesting to look at the connection between what we've been doing in our quantum field theory and our relativistic quantum theory, and try to make a connection with non-relativistic quantum mechanics. Okay, and the way we can do that is to look at, say, the scattering of distinguishable fermions. Okay, so and in the non-relativistic limit. Okay. And what we're going to try to do is we're going to try to compute our process, compute the amplitude, write down the amplitude for our process, and then take the non-relativistic limit and compare that with what we would have gotten from non-relativistic quantum mechanics, and try to extract the form of the potential, right? The electromagnetic potential. Okay. Let me just show you how it works. Okay, so what we'll do is we'll write down the amplitude for this scattering process, and then we're going to compare it in the non-relativistic limit to the Born approximation. So I'll remind you what the Born approximation is in just a minute. Okay? And from that, we should be able to extract the form of the potential that's created by this Coulomb interaction. The Coulomb interaction that we've written down in our quantum field theory. So let's look at this case. Okay, so we'll just consider this case, and let's just say that we can distinguish these particles, so we don't have to worry about any cross diagrams or anything like that. Okay. So if I use my QED Feynman rules, right? So I've got two factors of the vertices, and here you can see I'm taking tracing along this line first. So this is U bar of P prime. And then I come down here, this is gamma. There's a gamma matrix here. And what I usually do is, so you would draw the diagram like this, right? And then I usually put in little labels like this where I would say this is mu and this is nu. Okay? So then I would say come in here, so I've broken this diagram into this vertex, a propagator, and this vertex. So I come in here and hit this gamma matrix, and it has the index mu. And then come back down through here and it gives me mu. Right? Then I have the propagator, the photon propagator, and it's minus Ig mu nu. Right? We know this thing has to be a scalar, so if you're doing things correctly, the vertices will be, have indices up, and the propagator will have down, or vice versa. It doesn't matter, okay? Whichever way you feel comfortable. And then it traces along this line. It gives me this gamma nu piece. Okay. All right. So remember, we want to try to work in the non-relativistic limit. Okay. So that means that we only need to keep terms to lowest order in the three momentum. All right. So we can approximate the four vectors for these initial and final states as the energy component just being the rest mass, and the three components being P or K or whatever they are. Okay? We're not taking the completely at rest limit, we're taking the non-relativistic limit. So we still have these momentum to deal with. All right, so let's look at, what we're going to try to do is reduce this amplitude to its non-relativistic form. Okay? So the first thing I do is I look at the piece from the propagator, right? The P prime minus P squared term. Right? Remember, these are four vectors. So what I'm doing is dotting this four vector to that four vector. But P prime, the zero component, and P, the zero component, are both in mass, so those cancel each other out. So I get zeros in the zero components. And so then I take the dot product and I get the minus sign because this is coming from the spatial piece of the four, the dot product of two four vectors. Okay? So this is what I get. Okay, I get the absolute value of this vector thing squared. Okay. And then you got to go back a ways and remember how we wrote these when we were trying to what were we trying to do? Prove Lorentz invariance, I think maybe, or write down. No, we were trying to solve the Dirac equation, right? So we solved it in the rest frame and then we boosted it. Okay. So in the rest frame, so remember, in the rest frame, we're very close to the rest frame. These spinners, U and U bar, we broke down in terms of these C spinners. And remember, these C spinners can be like, you can align them so that they're the spin up and spin down along the Z-axis if you want. And and this factor square root of them, you have to go back and look. We put this in by hand, right? We put it in by hand because we wanted this thing to be Lorentz invariant. Right? And it turned out that we needed this factor, okay? So we just put it in by hand. Okay, and these C's are normalized so that they follow the usual orthonormality condition. Okay. All right, so that means, so let me plug these into, we have these two spinner products, this one and the other one with the gamma nu. Okay, so let me take the non-relativistic limit of this thing. Okay, so I get two factors of the square root of n. Right? And then I get the rho vector, and then I have the gamma zero that comes from this U bar. Remember, U bar is U dagger times gamma zero. Here's my gamma mu, and then here's the C, the column vector. Okay? And when I multiply that out, I need to consider different cases, mu equal to 0 and mu equal to I. Okay? If mu is equal to 0, then this thing just multiplies the other gamma 0 and you get 1. Right? And so then you can just multiply these two, and it gives you a sum of two terms. So you get 2 times the mass times this product, and that product is just a delta function. Okay, so that's the mu equals 0 part. The mu equals I part, you have to do the same thing, right? But there you recall that the gamma I is written in terms of Pauli matrices, right? So if I multiply that by gamma 0, I get something like this, and it's diagonal, but they differ in signs, okay? So that means that when I plug this in into this multiplication, this thing, that I'm going to get things canceling out. Okay, so for the mu equal I piece, these guys give me 0. Okay, so they vanish. So the only contribution we get to the full amplitude, let me go back to so this is what we started with. Okay, so what we found is that the only contributions are coming from mu equals nu equals 0. Okay, so that means that my amplitude reduces to something like this. Right, and gamma's or G00 is 1. Okay, so I've reduced it to this.
Minus
No, gamma's G00 is 1.
1. Oh, yeah, because it's
East Coast. Yeah. Okay, so we end up with this thing. All right. Now, what we want to do is try to compare this to the scattering amplitude that we would have computed in the Born approximation from quantum mechanics, non-relativistic quantum mechanics. Okay. And that, if you remember, is written like this. Okay. So you're always interested in computing there the T matrix, right? And so the Born approximation is just this, okay? And notice that we're working in momentum space here. Okay, so this is written in terms of momentum transfer. So this is still describing the same process, okay? And this is just a formula that you write down that it comes out of using the Born approximation. Okay? So what we had to do is we want to compare this to what we just got from this, from our QFT calculation. Okay? There's a couple of things we have to do. One is, remember we put these factors in by hand, okay, to get so that whatever expression we were trying to compute was Lorentz invariant. Okay? So in order to compare that to a non-relativistic thing, we needed to just drop those pieces. Okay? So we'll forget about those pieces. And over here, the delta function isn't going to have any effect on things that we're doing. So when we compare this expression to this, we end up finding that the Fourier transform, and so the momentum space potential that our QFT interaction produces looks something like E squared over Q squared. Okay. So what we have to do is, if we want the regular, normal position space, potential, which is what we would do in in normal quantum mechanics or normal electrodynamics, we need to take the Fourier transform of this. Okay? So if we want the potential in position space, we take the Fourier transform. Okay, and so you can do the angular part of this integral. It gives you this. You've probably done this integral several times now through quantum mechanics, maybe even this class. And then you have to use the contour integration, right? But you end up finding that, sure enough, the potential that you generate from our QFT QED interaction is nothing but the good old E squared over 4 pi r, okay? Which you learn about in grade school, right? And the fact that we started with, we were considering fermion scattering on fermion, we get an interaction that comes with a plus sign, so it's repulsive. Okay? But if you would go back and you do the same calculation for, say, electron, positron, you'd get a minus sign. Right? So that would tell you that the interaction between those two is attractive. Okay? So that's how you go from a full-fledged QFT or in this case QED quantity to non-relativistic quantum mechanics, but really in this case just classical ENF. Okay. All right. So that is that for the Feynman rules and whatnot. Okay. And what I wanted to do next is to get into the nitty gritty, right, and to really start computing some stuff. Okay. So we're going to start to talk about what Peskin calls elementary processes of QED. Okay? So we're going to be looking at, in this section of whatever you call it, we're looking at computing cross sections, okay, in QED. Okay? And so what we're going to do is we're going to start by considering the process E plus E minus annihilates into a pair of muons, mu plus, mu minus. Okay? And if you know anything about muons, you know that they're basically just heavier copies of the electron, right? So they're about 200 times more massive than an electron, okay, but they have the same quantum numbers as the electron. Okay? And so what we're going to find is that in order to compute the cross section for this process, we've already got all the tools, we've got all the formulas written down, right, for the cross section. We know how to compute matrix element from our Feynman rules, but we'll still need to develop a couple more techniques in order to compute, full-fledged cross section. But those, they won't take us long to derive or work through. Okay. Hey, you're just in time, right? All right, and so like I said, we'll start with E plus E minus goes with mu plus mu minus, and then we'll consider a few more simple QED calculations. But you'll see that, I put in quotation marks. You'll see that a lot of times once you've computed one cross section, you can get other cross sections by using something called crossing symmetry. Okay?
When was the last time in this class that you didn't put quotation marks around symbol?
Yeah, I
I
don't know.
can't remember.
I don't know. Anytime I see it, I just laugh. This is funny. Anyways, so we're going to consider, these are simple processes, okay? Okay, so we're going to start with E plus E minus goes to mu plus mu minus. And this is the simplest thing you could do. I mean, you could do E plus E minus goes to E plus E minus. That, it's the same thing, right? But E plus E minus goes to mu plus mu minus is very important even to modern day experiments. Right now there's not any electron-positron colliders running, but there will be in a few years the ILC, the Long International Linear Collider, which I guess is going to be built in Japan now. But they're going to collide electrons and positrons, okay? And so what they do is they accelerate the electrons and positrons to some energy, and then they collide them together, right? And they'll see stuff come out, okay? And what you need, though, anytime you set up a detector, at least this is what they tell me. I don't know, I've never done it, but you have to calibrate. You have to calibrate the detector, okay? So for cases where you're doing E plus E minus, the thing that you calibrate on is what's called the Z boson resonance, right? So you take E plus E minus and you smack them into each other, and it produces a Z boson. Right? And that Z boson has a finite lifetime, right? And so you produce the Z boson, and then it'll decay, right? And it decays into mu plus mu minus, right? But we learned a couple of weeks ago about this Bright-Wigner form of the resonance, right? So if you're looking at the cross section and you scan over the energy, you'll see this resonance, and the resonance would be right at the Z boson mass. Okay, and so that's where they use E plus E minus goes to mu plus mu minus to basically calibrate their detectors, right? To know that they're sitting at the Z boson energy. Okay, make sense what I'm saying? Okay. You guys are more experimentalists than me, so I don't know. But that's the importance of this, okay? All right, and so just some details, okay? So we're going to compute the cross section. For simplicity, we're going to consider the unpolarized cross section. In other words, we're not going to pass the electrons through any type of filter that would align their spins or anything like that. Okay, so these things are going to be completely unpolarized. All right, and for simplicity, we'll also neglect the electron mass. okay? And that's justified because, like I said, the electron's about 200 times lighter than the muon, okay? So it won't have any effects compared to the muon mass effects. Okay, so you're you know, completely justified in doing that. Alright? And for now, we'll be content to just compute the cross section to lowest order. Okay, so we're not going to throw in any loops or anything like that at this point.
I have kind of a naive question. The electrons, so two electrons are going to be coming in, and then they're going to interact with something, and
They interact with each other.
and they will produce the muons, and so which are an increase in mass. They're 200 times.
Yeah.
What causes the?
Because you're shooting these electrons at each other.
It comes from the kinetic energy.
Okay.
It's E equals mc squared in it's
Okay.
an example of that.
Okay. So the kinetic energy.
Yeah, that's the idea behind
It's
the
converted.
equalizer, right?
Yeah,
You know,
it's
like,
converted into mass.
you're always trying to produce heavy stuff, right? And so that's why they have to go to higher and higher energies, right? Because you're using, like Jordan said, E equals mc squared. Okay? Yeah. Okay, so let's get to it. Okay, so let's try to compute E plus E minus goes to mu plus mu minus. Okay, and this is where I'm going to make a break from Peskin because I just can't keep drawing Feynman diagrams from top to bottom. I always do everything left to right. Okay, so from now on, for me, time is going to go this way. Okay. All right, for Peskin, if you look in Peskin, everything goes up and down. He does time in the upward direction. Okay. So what we're doing is, so here's our Feynman diagram. We're colliding an electron with a positron. Right, they annihilate into an intermediate photon, right? And then that photon splits into mu plus mu minus. Okay, and the mu plus mu minus, like we said, we're pumping energy into the system so we can produce these heavier particles. All right. So this is the lone Feynman diagram that you can write down for this process. Okay, so we don't have to worry about any relative signs or any of that rubbish yet. Okay, so let's use our Feynman rules to write down the amplitude. Okay, so I start on the fermion or on the electron line over here. Okay, and so I start at this point. Remember, you always start at the end of the fermion flow. Right. So this an initial state antiparticle gives me a V bar spinner. So I write V bar, right, and I trace along and I get to this point, right, and this point gives me minus IE gamma mu. Right, notice I've already put in my little reminders that I'm calling this mu and I'm calling this nu. Okay, and then I keep tracing along, and at the end of this I get a U, right, it's a function of P. Then I can put in the photon propagator. I can actually put that anywhere, okay, but I always I always just put them in order. Okay, so I'm doing this. Then I have the photon propagator over here. Okay, so it's the G mu nu, and then I do the same thing for the muon line. So over here I have K. So I have U bar K. Come down and hit gamma nu, and then I have a V of K prime. And for the final state antifermion is a V. Okay, so at that point I can pull all my constants out front, and I can contract, the gamma, this G mu nu on one of the gamma mu's or gamma nu, right? And so my amplitude looks something like this. Okay. And these parentheses are optional, but I like to put them in there because it reminds me that this is one line, one fermion line, and this is the other fermion line. Okay. So we'll see that there will be cases where, your final state fermion line will connect to your initial state fermion line. And so the combination of U's and V's and all that stuff will be different. Okay. So I just like to put parentheses around these things, and you'll see why in just a minute. Okay. All right. So that's it. So that's the scattering amplitude. right? But that doesn't really tell us anything, okay? But you can still stop and pat yourself on the back and say, I just wrote down a QED amplitude, right? But now comes the hard part, right? Now we need to take this thing and multiply it by its Hermitian conjugate, okay? And so first we have to figure out what the Hermitian conjugate is, okay? So what we want to do is we want to compute the Hermitian conjugate. Peskin, and I guess I do too, get a little sloppy with the difference between Hermitian conjugate and just complex conjugate, but just know that we're talking Hermitian conjugation, okay? So what we want to do is we have to find the Hermitian conjugates of these things, the things in parentheses, these strings of spinners, okay? So let me look at this one in particular, okay? All right, so I know that when I have this thing, I take the Hermitian conjugate. So first what I did was I took V bar and I wrote it as V dagger times gamma zero. And then I take the Hermitian conjugate. What it does is it takes the Hermitian conjugate of everything, but it also reverses the order, right? That comes from quantum mechanics. Okay, so my V dagger is over here, it's a V now, and I get gamma zero dagger, gamma mu dagger, and then finally U dagger. Okay?
But dagger should reverse order, like conjugate reverses. Dagger is transposing and conjugating. So transposing reverse order and conjugating just does conjugation. No?
Well, I missed the first part of your question. What?
I mean, why conjugation reverses order? Because usually dagger or transposing.
Yeah. That's what I was saying. That I'm being a little sloppy here when I say M star. It's really M dagger. But Peskin does the same thing. That's what I was saying. That
Oh, but n is just a number. So star and dagger is the same, right? N is just a number. It's result of product of
yeah,
a vector to the vector, and it gives us number. Right?
yeah, it is a number, but
Like or single operator, not vector or matrix operator. Just right. And yeah, then dagger and conjugation is the same.
yeah. But okay, yeah. But in the intermediate stages, yeah, I think you're more. What you were saying before is probably more correct. Though, when I write something like this, I should probably write dagger. Right? It doesn't matter, but just know the difference. Okay. So what I'm doing is taking the Hermitian conjugate here. Okay. And so that's how I get this thing. Okay. So then I know that gamma zero dagger is just gamma zero, and gamma mu dagger becomes minus gamma mu. Right? But what I want to do is move this gamma zero over to here so I can make this a U bar, right? Because that's the Lorentz invariant form of the spinner. So what I have to do is pass gamma zero through here, and that gives me another minus sign because those things anti-commute. So it kills that minus sign, and so I get U dagger, gamma zero, gamma mu V, and this I can just turn into U bar. Okay, so the Hermitian conjugate of V bar gamma mu U is U bar gamma mu V. Okay? Everybody, all right? And likewise, you can go through the same exercise and show that U bar gamma mu V is V bar gamma mu U. Okay? So now we can form the matrix element squared. All right? So I got M times M star. Okay, so I get the couplings get squared. All right, so now up to e to the fourth over q to the fourth. And then here I'm taking, so this is where the parentheses become helpful. Okay, so I'm taking this thing times its Hermitian conjugate. Okay, and I put that in one parentheses. You'll see why in a minute. So it's V bar gamma mu U. I don't know if you guys can see that. V bar gamma mu U, and then U bar. It would be gamma mu V, but notice that I'm being completely general here. Okay, so here we have mu being contracted with each other. And I could, I mean, if I wanted to, I could write this as mu, but it it gets a little dangerous when you do that, okay? So to be completely general, when you write down the Hermitian conjugate of an amplitude, it's better to change the names of the indices, okay? Like we say, it's better to be more general than necessary, because in the end, there'll be identities that'll fix it for you, okay? All right, so the M squared looks like this, okay? So this is coming from the fermion line, so this is like the fermion line times its Hermitian conjugate. I mean, the electron line times its Hermitian conjugate. And this is coming from the muon line times its Hermitian conjugate, okay? All right, so at this point, we're still free to choose our spinners, right? Remember, we can define them however we want, okay? Or polarize them or align them however we want. In other words, we can make these things anything we want, right? Whatever spin state we want to start out with. So we can start with both the electron and the positron in the spin up state, or vice versa, or have some detector that requires that the muons be in a certain spin state. But that's not reality. Okay, so reality is that these beams of electrons, they don't bother polarizing them, okay? Because it doesn't really, for the most part, it doesn't really give you any information or help in any way. So they just have completely unpolarized beams and they collide those together, okay? So that means that when we compute the cross section, we should really average over the possible spins, okay, of the electrons, okay? And there's two possible spin states, so we're going to divide by 2, okay? We'll sum over the spin states and divide by 2, all right? And on the same kind of footing or same argument, the muon detectors are kind of blind to polarization. They don't really, they can't detect, the polarization of the muons. They're smacking into them. And so what we'll do is we'll just sum over all possible spins of the muon, okay? And we'll see that when we do this, the expression for this M squared is going to simplify a lot, okay? So that's, one of the reasons that we do it as theorists. And I've outlined kind of the experimental reasons, this thing, that they do it this way. But a lot of times, if you're looking for new physics, and you throw away spin information like this, you could be tossing out what's the saying, throw the baby out with the bathwater.
Yeah.
I mean, you could be throwing out some important stuff, right? So a lot of people push for trying to keep track of spin correlations. So, keeping track of the spin information, okay? Because that can tell you something about intermediate states.
Is it a limit on the technology of a detector, or is it?
Yeah. I mean, it's harder to do,
Just increase.
but it's
power necessary.
I would say it's split mainly. It's split between a little bit on the technology side, but a lot of it is on the theory side. A lot of it is because it's just harder to compute stuff if you're trying to keep track of the spin. Okay, and so that's why theorists throw it away. But if you keep track of the spin information and then compare it with results from an experiment, sometimes you can extract some interesting things. Okay. All right. So what we want to do is we want to take M squared, okay, and so S and S prime are the spins of the electron and the positron. Okay, so you can see I'm averaging over them, so that's why I'm summing and then dividing by 2. And R prime are the spins of the muon, so I'm just summing over those guys. Okay, and this is where these things that we learned about these spin sums, if you remember, these are where these things come in very, very handy, and I told you at the time that you would come to appreciate them. Okay, and it's because that when we take these sums over these spins, we're going to be able to replace these strings of U's and U bars and V's and V bars with these P slash plus or minus N pieces. Okay. All right, and let me just show you how this works really quickly. Okay, so let's consider one of these pieces of the M squared. It looks like I'm working, so I'm going to consider this piece right here. Okay, so this thing is going to be averaged over the electron and positron spins, right? Okay, so it's this term. Okay, and what I want to do is I want to remember these guys have implicit spinor indices, right? And so what I want to do is put those guys back in. Okay, so if I put them back in, and here's my sums over S and S prime. Okay, so you see V bar A, gamma A B, blah 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 blah, all the way on, all the way to the end. Okay, and if I want to use those spin sums, I need to get these guys in order. Right? I need to put the V's in front of the V bars, the corresponding V bars, and the U's in front of the corresponding U bars. Okay, so I look and I see, okay, my US of P is in front of the U bar S of P, so that's okay, I can keep that there. This guy I need to move to the front of the line. Okay, so I can freely do it because I've put the spinor indices, I can move stuff around. Right? So I put it over here, right? And now I can use my spin sums, right? So let me put the spin sum, or the sums, bring them in, right? So here's the sum over this V bar, or V bar, right? And then I have the gamma mu piece, and then I have the sum over S of U bar, and then finally my gamma nu. Okay. So now I can do those spin sums, right? And this guy will give me a P slash minus M, or P prime slash minus M, right? But it'll have spinor indices dA. And I can do the same thing for this guy to give me P slash plus M, as spinor indices PC. But then now you look at these spinor indices and you see that they cycle in on themselves, right? It goes D, A, AB, BC, CD, right? And then starts at D again. And that's nothing but the trace, right? So you can take out those spinor indices and rewrite this thing after you sum over the spins as the trace of P prime slash minus M gamma mu P prime slash plus M times gamma mu. Okay? You don't look convinced. No?
It's okay.
Okay. Just go through it and convince yourself. Okay? So all I did was took our expression, what we had, I put our spinor indices back in, right, which allows me to move stuff around. Move that to the front of the row, or the front of the line. Use the spin sums, right? And then note that when I see indices cycling on themselves, that's telling me that what it's doing is that it's computing the trace. And so I just replace those indices with an explicit trace operator. All right, and likewise, you can do the other string, the string from the muons, and you get something similar. Okay. So these should be both being proper. These would be mass of electrons, and this would be mass of muons. Okay. So now I can put it all together. Okay, and this is the way we would write it. Okay, so I'm computing the matrix element squared. I'm summing over the final state spins and averaging over the initial state spins. Okay, so that's where the factor of 1/4 comes from. And here's the factor of 1/4 right here. Now the amplitude squared is just the product of these two traces. And what you see is that the U's and the V's have disappeared. Okay, and it's a much cleaner expression, and it's all in terms of gamma matrices now. Okay, so all we have to really do now is to figure out how to do these traces. Okay, and it turns out that this trick is general. Right, so anytime that you have any external fermions, and you have these fermion lines, you're going to be able to, you'll get to the point where you won't have to even do all that stuff we just did on the previous slide. You'll be able to write down the rules and know that when you compute matrix element squared, you need to take the trace. Okay, so you'll replace the U's and the U bars and all that stuff with these P slash plus or minus M's. Okay. So computing those traces is a thing that Richard Feynman called trace technology, which I thought was like a really cool name. And we'll do that next time. Okay, so it'll take a little bit to figure out how to compute these traces. But once we do that, then we'll have M squared in terms of a nice compact scalar, number that we can plug into our cross section formula. Okay. All right? Okay. All right, any questions on anything? I've graded your homeworks, but I keep forgetting, they're on my desk. But I'll try to bring them Monday. I'll let you guys, in Brownsville, I'll send you guys emails.
Thank you.
Okay. All right? All right, have a good weekend.
You too. Bye.
Yeah. 6 p.m.
Yeah. Yes.
You put this rock.
What comes?
Is it rock?
No, I hadn't.
Apollo.
No, I hadn't.
Apollo's flight.
I hadn't heard about that. He suggested it.
Yeah. I
Yeah,
just thought
yeah,
you-
if any place
You just don't want to walk across campus.
I mean, maybe